Today we're going to be blowing the lid off, quite literally, our study of conic sections, because you can see we're looking at hyperbolas, which are made of two separate curves, as opposed to our circles and ellipses, which are each one single curve. So the definition of a hyperbola reads very similarly to the definition of an ellipse. There's one key difference though. Okay. Where we saw sum in the definition for an ellipse, we see the word difference for a hyperbola. So it's the set of all points x, y in the plane, the difference of whose distances from those two special focus points is some positive constant. Okay. So for constructing an ellipse, remember we saw that cool way of doing it involving a string and two pins? Unfortunately, that doesn't work for a hyperbola because it's hard to take a difference physically with string. For the sum, it's easy to add the lengths. For a difference, we'd have to, cut the string. It just doesn't work. But that's okay. So let's dive in and see the standard form of the equation for a hyperbola centered at the origin. Again, as with the ellipse, there are two possibilities. Either we have x squared over a squared minus y squared over b squared equal to 1, or we have y squared over a squared minus x squared over b squared is equal to 1. So notice, important, the a squared is always in the denominator of the positive term. Okay, in the red equation, our first one, we see it's in the denominator of the x squared because that's positive. Here in the blue equation, it's in the denominator of the y squared because that's the positive term. Now that's a little bit different than when we were looking at ellipses. For an ellipse, the a squared was always the larger of the two constants. Here, a squared is the constant in the positive term. Similarly though, it does still determine the orientation. We'll either have a horizontal hyperbola or a vertical hyperbola. Now you can see in these two different diagrams there's a lot more going on than there was before, but let's keep our heads, let's see what we see and try and make sense of it. So first things first, there are some commonalities with our ellipses and our circles. You'll see there is a vertex and another vertex given to us by the a constant. There is a co-vertex and another co-vertex given to us by the b constant, and again we have these special focus points given to us by some constant c. If you look down here, jumping ahead, you can see that we have a relationship involving c, a, and b, so we can find those focus points once we know what a and b are. What's the new stuff here? Well, for an ellipse, remember we had the major and the minor axis. Here, slightly different. We have the transverse axis, which is the axis that runs and crosses over each piece of the hyperbola graph. We also have what we call the conjugate axis, which is perpendicular here to the transverse axis and importantly does not meet the graph of the hyperbola. We also, for a hyperbola, have a pair of asymptotes. You can see we have one slant asymptote and another slant asymptote, and those pass through the corners of this rectangle here. Okay. Now we're going to proceed here step by step. We're going to roll out each feature in successive examples, building up a fuller and fuller picture of what a hyperbola looks like. So I know it looks like there's a lot going on right now, but we're going to roll it out piece by piece. Let's, for good measure, consider our vertical hyperbola over here. Okay. Notice it's called vertical because the pieces of the graph open upwards or downwards. So we have this piece opening upwards, this piece opening downwards. In the horizontal hyperbola, we had this left-hand piece opening to the left and this right-hand piece of the curve opening to the right. Piece is not a terribly precise word mathematically. The word we'd prefer to use to describe our hyperbola is to say it has two branches. Like a tree. So a horizontal hyperbola has this left-hand branch and this right-hand branch, and the vertical has this upper branch and this lower branch. Let's finish marking up our vertical hyperbola. So we have the transverse axis, which remember runs across the branches of the parabola, intersects the vertices and the foci. And we also have the conjugate axis, which misses the graph entirely, but runs over the two co-vertices. It's so important, let's note it down. So the transverse axis passes through the vertices and the foci. The conjugate axis passes through the co-vertices. So just as before, we were able to interpret A, B, and C as distances. So the absolute value of the constant C is the distance from the center to a focus point. Absolute value A is the distance from the center to a vertex. Absolute value B is the distance from the center to a co-vertex. And as before, if you do the right kind of geometric argument, you can show that C squared equals A squared plus B squared. Before we move on to our first example, let's see those distances actually in one of these diagrams. So here is our vertical hyperbola. The distance from the center to the vertex is the absolute value of A. The distance from the center to the co-vertex is the absolute value of B, and the distance to the focus is the absolute value of C. One final thing I'll point out is this very special rectangle whose diagonals form part of our slant asymptotes. Notice that rectangle passes through the vertices and the co-vertices. So let's see our first baby examples of working with hyperbolas. So we're asked to find the vertices and foci of these hyperbolas centered at the origin. So for part A, we're told x squared over 16 minus y squared over 9 is equal to 1. Now, which term in the equation is positive? Well, it is the x squared term. X squared, x-axis, makes us think oriented horizontally. That's how it works. So x squared positive, that means horizontal orientation. So the picture we're expecting to see is something like our two branches opening to the left and right will have a vertex and a vertex, we'll have a focus, and we'll have co-vertex, co-vertex. So that's the picture we're expecting. We need to extract A, B, and C successfully in order to calculate those points. So remember, it's the positive denominator. It's the denominator of the positive term that gives us A squared. So A squared is 16. So that means that A is 4. B squared is the other denominator, which in this case is 9. So B is equal to 3. We can calculate using our formula c squared equals a squared plus b squared. If we substitute in, we'll get c squared equals 16 plus 9, classic Pythagorean triple, so c is going to be 5. So let's summarize what we've learned here about this hyperbola. So the center is the origin, because it was in standard form for being centered at the origin. Our vertices, notice, because we had a horizontal hyperbola, we were expecting the vertices to be on the x-axis. The vertices are given to us by our a term, so we'll have 4, 0, negative 4, 0. We weren't asked to find our co-vertices, but we may as well show off. Co-vertices we were expecting to see on the y-axis, given to us by b, so we'd get 0, 3, 0, negative 3 as our co-vertices. What are our foci? Well, they're given to us by c. They lie on the x-axis, so we'll have 5, 0, and negative 5, 0. And we're done. Okay? So for those particular points, it's really not that much different of a calculation than it was for our ellipses. I'm going to skip the working for part B because it's very similar to part A, but I will tell you the end result. So we're still centered at the origin. The vertices this time will be at 3, 0 and negative 3, 0, and the foci will be at, again, 5, 0 and negative 5, 0. I do want to look at C though, because it's a little bit different. Notice this time the positive term is the y squared. So because y squared is positive, that means the hyperbola has a vertical orientation. Right? Y squared being positive should make us think of the y-axis, should make us think vertical. So again, the little picture we're expecting is for our branches of our hyperbola to open vertically, upwards and downwards. We'll have vertex, vertex, focus, focus, and co-vertex, co-vertex not lying on the graph. So let's extract the information that we need. Remember, a squared is always in the denominator of the positive term. So a squared is 4, giving a is 2. B squared, in this case, must be the other denominator, 25, giving us b is 5. We can thus calculate using our relationship that c squared is 4 plus 25, giving c is square root 29, which for approximation's sake lies somewhere between 5 and 6. So we need to write down what we've been asked for. Again, the centre, looking at the equation, we know we're centred at the origin. Our vertices this time, because we have a vertical hyperbola, lie on the y-axis. They're still given to us by a, so I get a vertex at 0, 2, and a vertex at 0, negative 2, and our foci again lie on the y-axis. They're given to us by c, so we get a focus at 0, root 29, 0, negative root 29. Now in this next example, a lot of information is being conveyed to us graphically, and we want to write an equation in standard form for this hyperbola. So there's a few steps we have to run through, but then we'll be there. So first things first, notice it is a horizontally oriented hyperbola. My branches are opening to the left and to the right. So that helps me pick the right type of equation. Right, for a horizontal orientation, it's the x squared term that is the positive term. So this is the equation that we'll be working with. We now need to figure out what A, B, and C are. Well, we can read that off from the graph. Right, we have a vertex lying on the curve, and we also have been given this special rectangle whose diagonals lie along the vertical asymptotes and whose sides pass through the vertices and the co-vertices. So it must be the case that we have a co-vertex here and here. So remembering the vertices are given to us by the constant A. Okay, this vertex has coordinate 6, 0. So that tells me A is going to be 6. The co-vertex here has coordinate 0, 6. So that tells me that B is going to be 6. We don't need to work out C because C doesn't take part in the equation for the hyperbola. So substituting in here, we get x squared over a squared, 36. Subtract y squared over b squared, 36, is equal to 1. Let's think a little bit more about these slant asymptotes. So for a horizontal hyperbola, notice if I start at the centre and run along by A to get to our right-hand vertex, to reach the slope of the positively sloped asymptote, I need to run up by B. To reach the slope of the negatively sloped hyperbola, I need to run by negative B or fall down by B. So that tells us from our slope-intercept form for a line that we either get y equals b over a, x, rise over run for that slope, or y equals negative b over a, x, rise over run for that slope. Doing a similar sort of analysis for a vertically oriented hyperbola, we'll see that our asymptotes either have slope a over b or negative a over b. So those are the equations for the asymptotes that form part of our graph for our hyperbola. For the remaining examples today, we're going to be given the equation of a hyperbola and be asked to sketch a graph of the hyperbola. So I want to run through a little checklist that we can run down to make sure that we successfully complete that task. So first things first, looking at the equation, you want to locate the centre of the hyperbola. So far we've only looked at the centre being the origin, but in general it'll be centred at HK. We want to find the vertices by figuring out the constant A. We want to figure out where the co-vertices are. That will involve figuring out what B is. We want to figure out the foci. We need to find C, and we'll also want to know, hey, are we oriented vertically or horizontally? Step 2 is we want to draw a dotted line to create that special rectangle. Remember that passes through the vertices and co-vertices. Next step, use another dotted line to add in our slant asymptotes. And remember, those form the diagonals of the rectangle. Finally, you're going to draw the two branches of your hyperbola you're going to make sure that you pass through the vertices and approach the asymptotes. One last thing I'll say is that up here, when I said you have to worry about figuring out the orientation, technically if you've correctly identified where the vertices are, and therefore where the co-vertices are, the orientation will take care of itself because you're going to make sure that you pass through the vertices and approach the asymptotes. Okay. But a good part of any step one is figuring out what is the orientation of my hyperbola. You'll need to do that in order to figure out where your vertices are anyway. Okay, let's see our first example of starting with some information and getting to a complete accurate picture of the graph of our hyperbola. So we're told that our centre is the origin. So let's throw that down. I'll mark it with a curly C. We're told we have a vertex at 4, 0. So there is our vertex. I know that that means our transverse axis is the horizontal x-axis, and therefore my other vertex will be at -4, 0. There is my other vertex. We're given our focus lies at 10, 0, so that tells us we have a focus there, and we'll also have a focus on the other side of the centre at -10, 0. So first things first, because my transverse axis is horizontal, my vertices are on the x-axis, I know my hyperbola at the end of the day is going to look something like this, right? We have a horizontally oriented hyperbola. So let's note that down. Horizontal orientation. So that means we can pick the right form of our equation. For a horizontal hyperbola, remember it is the x squared term that is positive. We'll subtract the y squared term and set that equal to 1. So now we need to figure out what a, b and c are. Well, remember we can read off what these quantities are using distances from the graph. So a is the distance from the centre to the vertex. So for us, we can read that off from the graph as 4. C is the distance from the centre to our focus. For this graph, that is 10. We can now figure out what C is, B is, by using the fact that C squared equals A squared plus B squared. Substituting, we'll get 100 equals 16 plus B squared. Solving for B gives, in simplified form, 2 root 21, which is roughly 9.2. So our B is 2 root 21. We're asked to write our equation. So we'll start with our correctly chosen form. I'll substitute in a squared, which is 16. I'll substitute in b squared, which is 84, and set that equal to 1. So that is our equation. Let's now sketch the graph. We'll do this by adding in our co-vertices. So those are going to be on the y-axis. Our b was a little greater than 9. So we're going to have a b here. A co-vertex rather, there, and a co-vertex on the other side of the centre. I can now use my vertices and co-vertices to add in our special rectangle. It will give us our our slant asymptotes. As the diagonals of this rectangle passing through the origin, the centre of the hyperbola. And now I'm able to draw the branches of our hyperbola. So I need to approach the asymptote, pass through the vertex, approach the other asymptote. That's one branch taken care of. For the other, approach the asymptote, pass through the vertex, approach the other asymptote. Now it will always be the case that the vertices on the graph are the closest that the branches get to the y-axis. All I mean by this is that our branches never travel inside our rectangle. They come in, glancing blow, change direction. Okay. That's recorded here in step 4 by saying the branches are bounded by these lines, by the sides of our rectangle. Okay, well remember for the equation of our asymptotes for a horizontal hyperbola, the equations are plus or minus b over a times x. That's our rule for y. So substituting in, we get y equals plus or minus 2 root 21 over 4 times x. If we simplify, we'll just get plus or minus root 21 over 2 times x as our y. If you forget that equation, you can read it off from the graph, correct? We know the run over to the vertex is given by a. We know the rise is given by b, hence why we get b over a or negative b over a as the slope of our asymptote. Let's run through another example together of starting with some information about our hyperbola and getting a complete picture of its graph and also its equation. So again, we're told the centre, h comma k, is the origin. So let's throw that down, curly C. We're told the co-vertex is at negative 16, 0, or one of them is. So that is right there. That's a co-vertex. Now by the symmetry of hyperbolas, we know there will have to be another co-vertex on the other side of the y-axis at positive 16, 0. So that means that our conjugate axis is the x-axis and our transverse axis is the y-axis. So that's going to be our transverse axis. And remember, the vertices and the foci always lie on the transverse axis. So when we're told there's a focus at 0, negative 20, there has to be another focus up above at 0, 20. So wherever the vertex is, I don't know where it is, we're going to find it, but maybe it's here, here. We know the transverse axis has to pass through the branches of the hyperbola, so I'm expecting there to be a vertical hyperbola. So let's write that down because that's going to help us write down the correct type of equation. So it's vertical, so the y squared term is positive. So that's the equation we're expecting to find. Now this time I can read off B and C from the graph, right? B is the distance from the center to a co-vertex. So B in this case is 16. C is the distance from the center to a focus. So C is going to be 20. I can now figure out what A is using the relationship C squared equals A squared plus B squared. So substituting in, I get 400 equals 256 plus a squared. If I solve for a, I get that a is 12. So that means I can add on my vertices to my picture. Okay, so I should have a vertex on the transverse axis at 12, 0. That's one vertex, and another vertex at negative 12, 0. So before we sketch, we can at least complete our equation by substituting in. So I get y squared over a squared, that's 144, subtract x squared over b squared, that's 256, is equal to 1. That's our equation. Let's now throw down our special rectangle so we can use the diagonals to get our slant asymptotes. The special rectangle always passes through the vertices and the co-vertices. I'll now put on the diagonals for our slant asymptotes. So we want to pass through the centre, hit the diagonal corners to get our slant asymptotes. And now I can sketch the hyperbola, its branches. I'm supposed to approach the asymptote, come in, meet V, rather the vertex, and then approach the other asymptote for one branch, and then do the same thing for the other branch. I think I forgot my arrows on my first example. You'll just have to forgive me. Okay, so we're asked to write down the equations of the asymptotes. Well, we could read off from the graph what the rise over run is, or maybe we remember for a vertical hyperbola, the rule is y equals plus or minus a over b times x. If we substitute and simplify, we'll get y equals plus or minus 3/4 x for our slant asymptotes. Let's spice things up a bit. Let's have our hyperbolas not be centred necessarily at the origin. Let's say we want to centre at the point h, k. Now really we're just taking that special case centred at the origin and translating horizontally by h units and vertically by k units. So it should come as no surprise that we just take our original standard form equations we were looking at previously and do a little transformation to them. So x gets replaced with x minus h, y gets replaced with y minus k. The horizontal orientation still works the same way, as does the vertical orientation. A, B, and C can still be interpreted as distances on that graph from the centre to our vertices, our co-vertices, our foci. The one thing that looks a little bit nastier is the equation of our asymptotes, but all we've done is done that same transformation to x and y in the equation for the asymptote. So before, for our horizontal orientation, it was y equals plus or minus b over a times x. Same deal here, except we've now got a minus k and a minus h in play. Similarly for the vertical orientation also. So we're kind of trying to just simplify matters here and say it's the same as before, we just attach h to x and k to y. So let's see an example in action. So we're given an equation and asked to find all the relevant points, the centre, the vertices, the co-vertices, the foci, and the asymptotes, and then sketch the graph. So first things first, let's look at this equation. The positive term is the y term. So it's going to be oriented vertically when we sketch our hyperbola. We need to read off the correct centre. Now, the x term gives us the x coordinate of the centre, So we're going to have a negative 6x coordinate. The y term gives us the y coordinate of the centre. So we're going to have 8 as our y coordinate. So let's plot that on the graph. Negative 6, 8, right here. Let's label it with a curly C. I know it looks like an E, but trust me, it's a curly C. We now want to find the vertices and the co-vertices and the foci, all that good stuff. So for the vertices, we know they're given to us by the constant a. So we need to notice from our equation, a squared is the denominator of the positive term. So a squared is 25. So that means that a is 5. Now, because we've decided this is a vertically oriented hyperbola, I know the transverse axis is going to be vertical. And so my vertices are 5 units away from the centre along the transverse axis, right? A was 5, that's our distance from the centre to the vertex. So I'm going to go from 8 up to 13 for one vertex and 8 down to 3 for our other vertex. So now we can read off our vertices occur at negative 6, 13 and negative 6, 3. Same deal for our co-vertices. Need to know what b is. I get to read off b squared is 36. So b is 6. For my co-vertices, I need to travel 6 units in this time horizontally away from the centre. So I'll end up starting at negative 6, negative 8. I'll move here 6 units right and hit our co-vertex at 0, 8. I could have started at negative 6, 8, the centre, and gone 6 units to the left. That would have given me negative 12, 8 as my other co-vertex. Because we're travelling, remember, B from the centre to get our co-vertices and A from our centre to get our vertices. What about our foci? Well, we need to know what C is. Using our old relationship, c squared is a squared plus b squared. Substituting, we get c squared equals 25 plus 36. So c is root 61, which is roughly 7.8. So let's travel c units away from the centre to find our foci. We know they're going to be on the transverse axis, so let's go a little less than 8 units vertically upwards, so that would get me to just shy of 16, and a little less than 8 units downwards from the centre, that would get me to just above the x-axis. That is our other focus. So our coordinates of our foci are going to be, the x-coordinate stayed the same as negative 6. I did 8 plus root 61. And then I did 8 minus root 61 to get our other focus. We now need to find, draw on our asymptotes. So remember, we draw our special rectangle, making sure we hit our co-vertices. We travel through those, and we travel through our vertices also. And then it's the diagonals passing through the centre that give us our asymptotes. And now we're in good shape. We can draw the branches of our hyperbola. So we're going to approach the asymptote, pass through the vertex, approach the other asymptote, approach the asymptote, pass through the vertex, approach the other asymptote. Now, to find the equations of these asymptotes, in practice, I am very unlikely to remember these formulas. I would rather just work it out from our graph. Okay, so we need to know the slope of the asymptotes. So our slope is going to be plus or minus rise over run. Okay, so the run forward is b. So that's our run. And our rise, depending on if we rise up to slope upwards or fall down to fall downwards, will be a rise of plus or minus a. So that's why we have that there. So here, our slope is going to be plus or minus 5 over 6. We have a point on the asymptotes, the center. Remember, that was negative 6, 8. So now all we need to do is point slope form using this information. So technically we'll do y minus k equals plus or minus mx minus a. There were two possibilities, right? Our center was y minus 8 equals positive 5, 6, x plus 6, or y minus 8 equals negative 5, 6, x plus 6. If you want, you could simplify this, distribute the 5, 6, so the negative 5, 6 gather, if we want it in slope-intercept form. But for the sake of time, we'll leave in this form for now. Let's see a few more examples, because practice makes perfect. So here, we're given the equation of our hyperbola. We want to find all those classic points and sketch the graph. So first thing that jumps out at me is the positive term is the x term. So we're going to be oriented horizontally. And I can read off that the center is 3, negative 6. Right there. So that's my curly C center. Now we need to know the vertices. Well, a squared is 9. So a is 3. Now because we're oriented horizontally, the transverse axis is going to be horizontal, and so that is the line, the horizontal line on which our vertices and our foci will lie. So to get our vertices, I need to travel 3 units to the right. Oops. Here's one vertex, and then 3 units to the left. Right there, that's my other vertex. So reading off the coordinates of those points, I get 0, negative 6, and 6, negative 6. For our co-vertices, we need to know what b is. B squared is 49, so b is 7. I'm going to run 7 units up above the center to get one of my co-vertices, and for the other I'm going to run 7 units down, so that will give me my other co-vertex there. Reading off the coordinates, I get 3, 1 and 3, negative 13 as our co-vertices. For the foci, we need to know what c is. C squared equals a squared plus b squared. Substituting, I get 9 plus 49. So c is the square root of 58, which is roughly 7.6. So for my foci, I should be going a little more than 7 units to the right and left of the center. So if I go 7 units to the right, I should end up just shy of 11. And if I go 7 units to the left, I should end up just shy of negative 5. as my x coordinate. So these are our foci. We now need to draw in our rectangle to find our asymptotes. So we'll pass through the vertices, the co-vertices, to produce our rectangle. And now for the asymptotes, pass through the diagonal of this rectangle. Isn't this fun, guys? Aren't you having fun? Doesn't this feel like we're doing art together? Now we're good to draw the branches of our hyperbola. I need to approach, oops, let me do it in proper pen. Need to approach the asymptote, pass through the vertex, approach the asymptote. I need to approach the asymptote, pass through the vertex, and approach the asymptote. There we have it. For the equations of the asymptotes, it's the same deal as before. We can just do point slope using the fact that rise over run, right? Run forward by A, rise up or down by B gives us plus or minus 7 over 3. That's our slope. Our point we can take on the line is the centre at 3, -6. If you want to use point slope form, right, it's going to be y minus k equals plus or minus x minus h. Jumping ahead, you'll either end up with, if we actually solve this time, we'll get y equals 7/3 x minus 13 for the positively sloped asymptote, or y equals -7/3 x plus 1 for our negatively sloped asymptote. Let's do one last example together that's going to tie all of this together. So we're given an equation and asked to sketch its graph and to state the eccentricity. Now this equation is not in standard form, so we need to do something to put it in standard form. What is that thing we're going to do? We're going to complete the square. Remember we did that for our ellipses. Similarly, we're going to do it right now. We're going to complete the square for the x terms and the y terms and leave the constant just chilling for now. So let's pull out the common factor of the x terms that I see, namely I've got a 4, that leaves behind x squared minus 6x. I'm going to leave a gap, right? Because I want to know, what do I need to add on here that will make this into a perfect square? That's the real question here. So let's not fill that in yet, let's work the rest of the line first, but that's really the question we're trying to answer here. For the y's, okay, I'm going to pull out a common factor of -25. That leaves y squared minus 10y, and we're going to want to add on something. I'm going to erase my y-axis for now. I'll put it back later, don't worry. Okay, but the same question, what do I want to place here that will make this term into a perfect square? And then sure, okay, I have this minus 489 hanging out by itself, and it's still all equal to 0. Well, hopefully we're getting pretty confident now at spotting what constant I need to add to make a perfect square. Here, in our x bracket, I'm going to need to add on that 9. Okay, that will make sure that that bracket can be factored as x minus 3 all squared. Okay, if you don't see how we did that, remember that -6 coefficient of x. We're going to divide by 2 to get -3, and then we're going to square to get 9. that is what we place in the constant term. Okay. However, I've added something, so to make sure our equation is still true, I need to subtract that same quantity elsewhere. So that 4 times 9 that I've added inside on that left-hand portion of the left-hand side will need to be subtracted to make sure our equation is still balanced. Inside our blue bracket for our y to complete the square, I'm going to have to add 25, right? Because I've got that negative 10 coefficient of y, I'm halving it to get negative 5, I'm squaring to get 25. I then need to make sure that our equation is still balanced, so I need to add on 625, right? 25 times 25. So we've completed the square. Let's see what our equation now looks like. We have 4x minus 3 all squared minus 25 y minus 5 all squared is equal to, if I do the arithmetic, I'll end up with negative 100 on the right hand side. Now we're making progress, we're getting closer and closer to standard form. The one red flag that I currently see is my right hand side is not 1, it's negative 100. So to really be in standard form, that right hand side needs to be 1. So let's divide everything in sight by negative 100. So when I do that, we end up with, okay, the whole point was we wanted the right hand side to be 1. Now I'll end up on the left hand side with y minus 5 squared over 4, subtract x minus 3 all squared over 25, just with the cancellation that we were expecting to see. Now, I want to point out, before we go any further, something kind of sneaky happened. Before we made that right-hand side equal to 1, the positive term on the left-hand side was the x term, the square of the x bracket. However, dividing by that negative interchanged the roles. So in our standard form, what was the positive term? Well, it was the y bracket. So if you're not paying attention to the sign of the right hand side, if you have made sure that it is 1, you might end up orienting your hyperbola incorrectly. Okay. But here we are, this is in standard form, and so now we can start sketching. So this is the equation that we're going to be working with. So what do we need to know? Well, certainly it is vertically oriented because it's the y bracket that is positive. What is the center? Well, I can read it off. The x coordinate comes from the x bracket, and the y coordinate comes from the y bracket. So the center is at 3, 5. So 1, 2, 3, 1, 2, 3, 4, 5. There is our center. Let's figure out what A and B are so we can see the vertices and co-vertices. A squared is going to be 4, so that means that A is 2. B squared is 25, so B is 5. Now remember, our hyperbola was vertically oriented, so the transverse axis is going to be vertical. So my vertices are going to be 2 units vertically above and below the center. So we'll go 2 up and 2 down. Those are our vertices. Our co-vertices are going to be 5 units to the right and left of the center. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Co-vertex, co-vertex. So if we read off those coordinates, we'll see the vertices have coordinates 3, 7, and 3, 3. The co-vertices have coordinates -2, 5, and 8, 5. What about our focus points? Well, we need to find C. C squared is a squared plus b squared. If we substitute in, we get 29. Therefore, C is root 29, which is roughly 5.4. So I want to go a little bit more than 5 units vertically above and below the center. So that would be 1, 2, 3, 4, 5, a little bit more for that focus, and then 1, 2, 3, 4, 5, eek, I've run away, but that's okay. Something like that for our other focus. Okay, let's deal with our asymptotes. So we need to draw in our rectangle that passes through the co-vertices and the vertices. Add in the diagonals as our asymptotes. And now we can draw the branches of our hyperbola. Approach the asymptote, meet the vertex, approach the other asymptote, approach the asymptote, meet the vertex, approach the other asymptote. Now, we weren't asked to write down the equations of the asymptotes. We could do it if we wanted to. We were asked to write down the eccentricity. So recall, for the eccentricity of an ellipse, it works for hyperbolas too. It's defined to be C over A. So for us, that is root 29 over 2. For completeness sake, let's write the equations of our foci. So I know I started at the center 3, 5. I travelled root 29 up vertically to get one focus. For the other focus, I fell down by root 29. So there we have it. All done. Good job.